Okay, here's the problem. You're given a list of numbers, all jumbled up, and you need to sort them. Smallest to largest. Simple to say. But by the end of this video, you'll be able to trace and write it from scratch. Because in an interview, they don't just want it sorted, they want it sorted or fast. And the algorithm they love to ask about, one of the most elegant sorting algorithms ever designed. Quicksort. So let's actually understand it, not memorize it, understand it. Here's the one idea behind quicksort. Just one. We pick one number from the list, we call it the pivot. We could pick any number as the pivot. For simplicity, let's always pick the last one. 5. Now here's the move. We go through everyone else and we ask one question. Are you smaller than 5 or bigger than 5? 7, bigger than 5, goes right. 2, smaller than 5, goes left. 9, bigger, right. 1, smaller, left. And look what just happened. 5 is now sitting in its final correct spot. It will never move again. Everything smaller is on its left, everything bigger is on its right. That's the whole trick. We didn't sort the list. We just put one number in its right place and split the problem into two smaller problems. Now, we do the exact same thing to the left side, and to the right side, and again, smaller and smaller pieces, until every piece is just one number, and a single number is already sorted. That's quicksort. Pick a pivot, split, repeat. Now we're going to walk through one example, slowly, every single step. If this is your first time seeing quicksort, this is the part where it actually clicks. So don't rush, we'll do it together. A second ago, we just slid the numbers left and right. Now let's slow that down and see the actual trick the computer uses to do the sliding. Because that trick is exactly what will turn into code in a minute. Here's our list, 8 numbers all mixed up. 8, 3, 1, 5, 7, 2, 6, 4. Let's trace through quicksort, step by step. Our rule, the pivot is always the last element. So the pivot is 4. Now I'll use a little marker. Call it the wall. Like a fence, everything behind the fence is guaranteed to be smaller than our pivot. Right now it's empty. We compare one number at a time, left to right. First number, 8. Is 8 smaller than 4? No. 8 is bigger, so it stays where it is. The wall doesn't move. Next, 3. Is 3 smaller than 4? Yes. So 3 belongs on the smaller side. The wall moves forward one step, and now we swap. 3 and 8 trade places. 3 is in the smaller pile now. Next, 1. Is 1 smaller than 4? Yes. Wall moves forward again, and 1 swaps with the 8 that's sitting there. 1 joins the smaller side. 5. Is 5 smaller than 4? No. 5 is bigger. Wall stays. 7. Smaller than 4? No. Skip. 2. Is 2 smaller than 4? Yes. Wall moves forward, and 2 swaps with that 8. 2 is in the smaller group now. 6. Smaller than 4? No. Skip. We've now checked everyone before the pivot. Time to place it. We put the pivot, 4, right after the wall. 4 and 5 swap places. And just like that, 4 is in its final correct spot. It will never move again. Look at what we've got. Everything to the left of 4, 3, 1, 2, all smaller. Everything to the right, 7, 8, 6, 5, all bigger. We just put one number in its right place, and we split the problem into 2 smaller problems. 3 numbers on the left, 4 numbers on the right. Now we go to the left side, 3, 1, 2. The right side, we'll come back to it. One thing at a time. New pivot, the last one in this piece, 2. 3, is 3 smaller than 2? No. 3 is bigger. Wall stays. 1, is 1 smaller than 2? Yes. Wall moves forward. 1 and 3 swap. Now place the pivot. 3 and 2 swap. 2 is locked. Left side has just 1. Right side has just 3. Both single numbers. 1 is on its own. A single number is already sorted. That's our base case. Locked. 3 is on its own too. A single number is already sorted. That's our base case. Locked. Now the right side, 7, 8, 6, 5. New pivot, 5. The last one in this piece. 7, is 7 smaller than 5? No. 8, smaller than 5? No. 6, smaller than 5? No. Nobody was smaller. So we place the pivot, 5, right at the front. 7 and 5 swap. 5 is locked, nothing on the left. 3 numbers on the right, 8, 6, 7, 8, 6, 7. Pivot, 7. 8, smaller than 7? No. 6, smaller than 7? Yes. Wall moves, 6 and 8 swap. Place the pivot, 8 and 7 swap. 7 is locked. 6, on its own. A single number is already sorted, that's our base case. Locked. 8, last one. A single number is already sorted, that's our base case. Locked. And look at that. 1, 2, 3, 4, 5, 6, 7, 8. All in order, every single number in its correct place. 8 rounds. Each round put one number in its final spot. And each round the pieces got smaller. That's the power of this idea. Split the problem and the smaller pieces practically sort themselves. That's a dry run of quicksort. To see how all these rounds connect, let's look at the big picture. When we started, we had our full list of 8 numbers. We picked 4 as our pivot and split the list in 2. On the left, we got 3, 1, 2. On the right, 7, 8, 6, 5. And we split both of those sides again. The left split into single elements, 1 and 3, around pivot 2. The right split into 8, 6, 7, around pivot 5. We had just one more split on the right side, leaving single elements 6 and 8 around pivot 7. This is our recursion tree. Every block is a single sub-problem. Every level splits the work in half. Remember this shape because it's the key to understanding how fast quicksort really is. Now watch how they combine. 1 is a single number, already sorted. It's our base case. 3 is also already sorted, so they merge around pivot 2 to form the sorted list. 1, 2, 3. On the right, 6 is sorted and 8 is sorted. They merge around pivot 7 to form 6, 7, 8. This combines with pivot 5, giving us 5, 6, 7, 8. Finally, the left side, the pivot 4 and the right side merge. The entire list is sorted, every step we just did by hand. In a minute, we'll write the code that does this automatically. Alright, let's write the code. I'll type it the way you'd write it in an interview, slowly explaining each line. First, our main controller, def quicksort, taking the array and low and high bounds. Before doing any work, we check if low is less than high. This is our base case. If it is, there is more than one element to sort. We call partition to split it. This puts our pivot in its correct spot and gives us back its index pi. Now we call quicksort recursively on the left side, from low to pi minus 1, and recursively on the right side from pi plus 1 to high. And that is the entire controller. Very simple. Now we need to implement the helper partition function. So def partition, taking the same parameters, r, low and high. We choose the last element as our pivot, r at index high. Remember the wall from our dry run. This is it. We set our wall boundary marker index, I, to low minus 1, meaning nothing is in the smaller zone yet. Now we run a loop with index j, scanning from low all the way up to high. Every time we find a value r that is smaller than our pivot, we slide our wall one position to the right by incrementing I and swap the smaller element at j into our smaller zone at index I. If the element is larger, we do nothing, and the scanning point at j simply moves on. Once the loop finishes, we swap our pivot from the very end to right after the wall. This places the pivot in its correct sorted position. We then return that index I plus 1. And that's it. 2 clean small functions. One splits the array, and the other recursively delegates the sub-problems. This main guard block simply tells Python to run our quicksort function when we execute this file directly. We set up our test array and run quicksort. Let's save the code, exit out, and run it to verify. Before I hit enter in the terminal, pause for a second. Can you predict what the output will be? Let's run it. Running quicksort. Splits at pivot 4, splits at pivot 2, splits at pivot 7, and there is our sorted output. So how fast is this algorithm? In the normal case, each partition splits our list roughly in half. If we draw this out as a recursion tree, it splits into 2, then 4, then 8. Because we divide the list by 2 at each step, the depth of this tree is log n levels. And at each level, the total partitioning work across all subproblems is always in comparisons. So multiplying the work per level by the number of levels gives us a total time of n times log n. On log n is incredibly fast. For a million numbers, that's only about 20 million steps, not a trillion. But what if we get unlucky? If we feed quicksort a list that is already sorted, and we always pick the last element as the pivot, every split only peels off a single element. Our balanced tree collapses into a completely lopsided chain of n levels, with n work at each step. This forms a triangle of work. Its area is n times n, dropping our speed to on squared. In practice, we pick our pivot randomly to avoid this exact trap. And that is the key concept interviewers are listening for. If you can explain how pivot choice shifts, quicksort from a balanced n log n tree into a degenerate n squared chain, you truly understand the algorithm. That's quicksort. See you in the next one.